I would like to talk about Nanosystems. This is a part of the program that I'm running. This is sponsored by an ERC senior grant. And I'm actually showing different technologies that I'm dealing with. And they're all connected together. Let me start by giving a general motivation of this work. I do believe that as engineers, we are here to solve problems for real life, for the people. I think that today there are many societal, many economic problems that can be addressed by the proper use of technology. Some of these have been object of numerous discussion, for example, at the World Economic Forum that meets in Davos every year. And I like to focus on 4 topics that are extremely important for the economy and society, where actually electronic and information science can have a big say. One is strengthening the welfare, because we want to have better and affordable healthcare. Wellness also is an important issue. We have to deal with aging population, we have to deal with childcare, and again, technology there can be very important. Another important issue is mitigating risks. The picture you can see there, even though it's small, shows Fukushima after the blow-up of the roof of the nuclear reactor. My previous life was a nuclear engineer here, and we all know that there are risks, there's risk analysis, there are risk factors. It's extremely important to use technology as a way of mitigating risk. Some accident may happen, but the consequences of the accidents can be actually controlled very often, and it can be done, for example, by being able to monitor the environment. Next important issue is sustainability. Sustainable society, it's important. Having energy in an efficient way for everybody, having water in an efficient way for everybody is extremely important. We all talk about energy. Energy is a hot item everywhere, in Silicon Valley, in Italy, in Europe, in Japan. Very few people talk about water, but water is very similar to energy. Having water of good quality for everybody and controlling pollution is important. And finally, I think one of the key issues is enhancing security. We live in a cyber world. We have our money in soft forms through banks, through investment agencies. It's rare that today people rob a bank with a pistol, but it's more, you see more and more scams. You see more and more attacks to people. So the issue of how we would make our world secure in a cyber society is extremely important. Now, this talk is not supposed to be about politics and society, it's supposed to be about technology, so I will be focusing now on the technology, on the engines that actually we want to build. Important point that I want to say is that electronic and information technology are key to solving societal problems. When you talk about electronic systems, we very often think of microchips, of what actually was the engine of computers over the years. Nowadays, systems are more complex. They include sensing, they include actuation. Software plays a major role. You talk about people who have developed systems. They do realize that the effort in many years to develop the appropriate software is more than the effort put in hardware, because software is complex and actually deserves a lot of attention. System technology overall is built bottom-up from materials. Today we are seeing tremendous advances in understanding materials, understanding the properties. It's possible to have functional materials and devices that are built on the material themselves. Actually, this is what opens up the interest in nanotechnology for people who have the habit of working with system engineering. So often I talk about nanosystem. What do I mean by nanosystem? Well, the word nano relates to nanoelectronics. That is CMOS beyond the 32 nanometer node. Now we have devices in the 20 node. People are experimenting with the 15 nano node at the time. But it's important to remember that CMOS is not the only technology which is there. There are other technologies that are close to production, and they include the use of silicon nanowires and carbon nanotubes. And another important aspect of nano is the so-called nano biosensing. There is a size compatibility between the devices that we build in electronics and some of the bio objects that are of interest to us, like DNA, proteins. And therefore, it's possible through specific electrochemical system to do efficient detection and monitoring of living bodies. Now, when I talk about systems, systems have inherent difficulty because they're heterogeneous. They involve parts of different kinds, and the complexity is inherent in the design and in the management of the system. The complexity stems from the fact that the systems are typically discrete. The problems of solving this discrete problem is typically intractable, and you have to deal also with large-scale systems. Much has been said about beyond CMOS. Here I have 3 pictures, actually 1 picture and 2 sketches. The first one is a nanowire transistor. Now, nanowire transistors use this gate-all-around transistor, so the gate is built around the nanowire, and it gives a much better ion over eye-off control, and therefore the possibility of having even more power efficiency when you operate at speed. The center picture is a sketch of a carbon nanotube. Carbon nanotubes have been object of a lot of investigation. So is graphene. I don't have a picture for graphene, but I have something similar actually because it's been something investigated by a colleague of mine at the PFL, which is actually MOS2. MOS2 is not another version of MOS transistor, but actually it's molybdenum disulfide. It's a very interesting material that can be layered like graphene, but it has a band gap, which for people who design transistor, of course, is a very nice feature. Big issues that we have. Can we mix and match these technologies with CMOS? We do know that we have made such a big investment in the fabs for CMOS that CMOS will not go away, will stay. So the question is how we can use these technologies as add-on to the standard processes. For example, CNT can be used in its metallic form as interconnect on top of CMOS. The issue is also what is the added value? Why should we use different type of material? I think that about 5 years ago, people involved in nanotechnology were thinking of these technologies as an alternative to CMOS, again thinking that CMOS will stop its scaling around the 20 nanometers. I've heard lots and lots of talks on scaling, and I think that these talks are wonderful because they are portable. Every 10 years, you can change the parameters and give the same talk again. So we think that now that basically the standard techniques like CMOS can be scaled down probably to the 5, 7 nanometer range. There is, of course, at some point some barrier, which is due really to the physics of the device. But that's scalable. So when you look at nanotubes or devices that are also in the range of 10 to 20 nano, it's not that the size is the major factor over CMOS. It's the fact that they may have other properties that are interesting, like, for example, higher mobility. And of course, the issue is what is the drawbacks of this type of materials? How we design with them? Are they easy to handle? Are they more durable? What is the reliability? These are very important issues, especially if you are designing complex systems. So, in the first part of my talk, I'll talk about nano devices. This again, it's a beautiful picture taken at the microscope of 3 suspended nanowires. And here again, I'd like to stress on the concept of nanowires and then CNTs. Nanowires are nice because they can be made out of silicon. So you can use silicon process that it's compatible with CMOS. It's done top-down. Also, talking about nanotechnologies, I do believe in the top-down approach. That is, as engineer, we engineer the different features. We will use some method that may be complex to do the lithography on the devices and will, in the end, architect the system. There are other schools of thought that think that you can design devices, the devices will self-assemble, and in the end, as a result of a complex self-assembly, you will get a complex system. Self-assembly works in a limited domain. I have my doubts that self-assembly will work at a scale in which you can make systems beyond billions of devices as we already have today, because in order to be competitive, you have to have the ability of putting together systems that are more complex than what you have today. So I do believe in a top-down approach. Again, this picture shows 3 of these devices. This picture shows actually how you can array devices to make crossbars of silicon nanowire transistor. Carbon nanotubes are also a very nice technology. When I talk about nanotubes, sorry, I will mainly focus on one process that's being developed at Stanford by Philip Wong and Subhashish Mitra. It's a process in which you grow the carbon nanotubes on quartz, use a tape process to detach the nanotubes from the quartz and bring it onto a wafer, silicon, and then you will use standard processing steps for CMOS to build devices, but the devices will have their channels done with carbon nanotubes. So that's a sketch of a transistor done with carbon nanotubes. Those kind of blue bars are the nanotubes that you will find under the gate of a transistor. So why would you do that? Why would you use a CMOS-like process where you just play a trick that your channel is made of CNTs? Well, the answer is that the mobility in the CNTs is much higher. So if you build small devices, that is in the order, for example, of 10 nano, then you would have a much higher current that can be switched by these devices. So if you have a capacitive load, you can go at speed even though you have small transistors. So that would be the advantage of using CNT within a CMOS process. Now, everything has a price. Now, if you look at the CNTs that are grown, that's a picture there, you will see that they are not really that nice. You have some curls that, of course, you wouldn't like to have, and then you have some broken CNTs, and then you have some other CNTs that are not straight. So suppose that things can get better, and you will have a picture in which you have CNTs that are continuous, but they are not all straight. You still have problems, even under this simplified model of fabrication. Because if you build a device like this and you have a CNT that goes in diagonal, as you see in the picture, you will have conduction where you shouldn't have it. So the transistor does not implement the correct logic function. So what do you do? At this point, if you use this type of process, you would have to use new design rules. This is a simple example in which you would use an etching step to remove the CNTs from one region. That will be an extra mask, and therefore you will remove the problems of having these additional transistors. Conversely, if you have a missing connection because the CNT are interrupted, there's nothing much that you can do with etching. So along this line, we developed a toolkit based on Cadence design system tools that we will let design small functions that's not too complex that will use actually this CNT technology as an underlying way of making transistors. In the sequel, I will mainly focus on silicon nanowires. I like nanowires better because I think they are much closer to the present and near future, and also because we can build devices with nanowires in the fab in our university, and so we can have a close feedback with what we get. We can do measurements. So they are typically done on silicon insulator wafers, and they can actually be built through a step of deep reactive ion etching. So it's a standard step, processing step that can be done. You will build these transistors that have this gate-all-around, as I mentioned before. The picture here actually shows two of these devices built on top of a silicon nanowire and a cross-section. Now, interesting enough is how do we position these nanowires with respect to the current technologies that the industry is using. As you know, there are two major trends. One trend which is followed in Europe is to go to this fully depleted SOI for the 20 nano, the 15 nano node, I would say more the 15 nano node than others. And then there's the Intel approach where they use FinFETs or 3D FETs. Of course, people use different names for the same concept. That's the picture that you will see on your right. Now, on the left, you will see the nanowires. You have more than one nanowires, one on top of each other. It looks very similar to a FinFET, except that the nanowire is round, so the gate can really go all around the nanowire, and therefore you have a very good control again of the ion over I-off of the transistor. So there's quite a bit of similarity, and it's also quite a bit of similarity in the sizes or in the cross-section of the silicon nanowires that we can obtain as compared to these devices done by Intel now. Our research in this domain is purely exploratory. I don't think that we have even the thought or the dream of replacing Intel technology. We are not a manufacturing company. So we do it really for the intellectual value of using this idea, but we think that other people may follow us with real developments for this type of devices. This is the cross section. If you cross this, you will see the nanowires going through. These are the central one, and you will, around the white area will be the dielectric that can be silicon dioxide or also can be hafnium dioxide. Now, why do we like to do these devices? Why don't we do something else? There are two reasons that excite me about using this type of devices. The first one is the property of ambipolarity. So that is, you can build devices whose characteristics are controlled by a backgate voltage, or else you can build devices that we actually have measured them, that have two gates. Actually, one gate determines the polarity of the devices, and the other one determines the fact that the device is on or off. So, thinking in terms of P or N transistors, you don't have P or N. A device can be either P or N according to the voltage that you put on a gate. So that actually is very nice because it gives you a lot of flexibility in doing these gates. These actually are curves, and if you look at these curves and their shift, you will see that on one side, on the right, that looks like an NMOS transistor, while on the left it looks like a PMOS transistor, and there's a transition in between due actually of the sweep of the polarity gate. In practice, we don't use this for doing any analog design. This is done for digital, so if you fix a polarization voltage, then the device will be either on or off according to the appropriate polarization. The second effect, which is interesting, is the memristive effect. Now, memristors were postulated by Leon Chua a long time ago. There's been a lot of talks about memristive effects after Stan Williams actually showed that with titanium dioxide you can make memories. Now there's an entire family of devices that use memristors or version of memristors to do storage. So that's extremely interesting. This type of characteristic can be measured also within the silicon nanowires. Remember that you can make the thing simpler if you think that the name memristor is too complex for you. If you take a device in the IV plane, if it's a linear resistor, you have a straight line. If it's non-linear resistor, you have a curve. If you have a hysteresis, you have a picture like this. This is nonlinearity with hysteresis, which is basically the same thing as memristor. So if you fix up a voltage of a bias, you can have two situations in terms of current flow, and one can be associated with storing a logic 0, the other one to storing a logic 1. So this actually is an extremely powerful idea to do memories, and actually there is a big move in industry toward going to this. The first incarnation is basically phase-change RAM. Phase-change RAMs are on the market today. And we think also that this type of nano devices can replace memories at some point in the future. Now I'll talk about circuits now, nanocircuits. What I like to do is to make an abstraction of what I've shown before with the technology and reason only on the abstraction. So why do I like the ambipolar devices? You have this polarity control, so you could have actually devices where instead of having the bubble, you have the bubble with the question mark. You can set the bubble to what you want by setting up the voltage. So you can make all kinds of devices, from the simple one, like NORs, to a more complex one. This can be done with the nanowires. They could also be done with the CNTs, but I'm not talking about CNTs today, so I really like to focus on the nanowires. Symbol that I use, it's a transistor where you have the control of the bubble, of the polarity. Now, why is this important? It's important because you can have in your device an inherent inversion capability. Think back of what you've learned when you have looked for the first time at CMOS gates, the gates that we use all the time, the static ones. The gates are an extension of the basic inverters. You have a pull-down network and a pull-up network. Since the CMOS gates are an extension of the inverter, they basically can implement only negative unate function. This is the main restriction of CMOS. If you use domino then, because it has its own inverter at the end, can only implement positive unate function. That's why you cannot build inverters with domino logic. Now, in this type of technology, you can have this local inversion, so you can build binate function like XORs, using the same complexity as you would have for doing NANDs and ORs. And actually here we have some pictures, starting from the very simple inverter that you could have, to the XOR, which is the second gate, which actually can be done in a very simple form using 4 transistors, we see an OR, and then we see a complex gate that actually mixes some inclusive and some exclusive OR. So this is extremely interesting because in my life I've always seen these two types of design. The design of the so-called random logic or logic that will go into finite state machine, which is typically based on Nansen ORs. And if you think of the reality today, when you design this, you use the tools, you use Synopsys, which is the major provider of the tools. All these tools are built to design with Nansen ORs. If you try to do something advanced that uses XORs, it will fail. You don't design a multiplier using the Synopsys design tools. I think I can say that, and Synopsys will not get after me because that's the truth. Conversely, if you are a fan of arithmetic circuits and you do XORs, you do majority, you do counters, use technologies that are different because you actually have these binate functions that are not monotonous. And so you have different style. Now with this type of devices, you can mix and match and can have something which is actually very convenient to implement your logic. And you can actually think of different logic families. This is the simplest one, where you actually use transistor pairs. The reason why you use transistor pairs is because you don't want to pay the price of the voltage drop that you may have. Otherwise, you have a voltage drop, you have a threshold drop if you don't use that. This is a simpler version where you would use fewer transistors with a pseudo load, and this is also simpler in terms of logic, but it will cost you more power. This is another type of device where you use single transistors, but on the other hand, you would have a threshold drop, so you need to have some driver in order to restore the signal, and this is a mixture of the two. Again, you can think of other families, you can think of dynamic logic built out of this. But the bottom line is that you have one more degrees of freedom that you can play with in the inversion because you can locally invert signals on your primitive, which is your logic gate. So in the end, you can make libraries of cells that are intrinsically more expressive in terms of logic. And so eventually, you can get logic that's more compact because your cell can express more. You would use less wiring. And you know that in the end, it's the wiring which is the penalty that you would have in terms of performance. So that's the advantage of using this type of technology. Of course, many things have to be proven. Many things have to be proven how these devices, how these gates can be used within specific architectures or nanoarchitectures. So thinking of what are the nanoarchitectures for the nanosystem world, you know, and learning from what people do in CMOS today with the 22 nanometer node, you see that things have to be extremely regular. Things look today, even though it's semi-custom design, they look like gate arrays because you want to have the wires very short and very predictable. So this would be, these are pictures actually done on a microscope using nanowires. You can see actually the vertical nanowires, these are done before the gates are placed, that are put in an array, because we do think that using an array structure can be extremely convenient in order to contain the variability of the wiring length, which is actually the killer in the design closure, because it takes a long time to get the correct timing on the different paths. What are the basic cells? The basic cell postulated to be used is the so-called generalized NOR or generalized NAN that actually can be built out of these specific ambipolar devices. And if you use them, these gates actually can be programmed in different ways to do specific logic functions. That it can be programmed via mask by just, for example, either grounding or putting to VDD some gates, or by just removing some devices. Or you could use this as a way to make an FPGA. You can make FPGAs by actually allowing some memory bits to set the polarity or set some gates to 1 or to 0, and therefore generating the cells that you would have, that you would need. So again, why would you need an extra brand of FPGA in a market that it's already very flourishing? Well, again, the idea is that you could have cells that can be expressive for both unate and binate functions, so you could implement logic in a better way overall. In FPGA, of course, the programming will be done after manufacturing, and again, it can be done in different ways, either using kind of anti-fuse techniques or using like sliding stars, basically some memories that would store the fuse maps and then will polarize statically the gate so that it will do the functions that are required. Now let me switch a little bit gear. I want to talk another part which is extremely important. It's basically connectivity in systems. Actually, this is the picture of the new freeway that will be built around Milan for the Expo, and that will let everybody drive without any stoppage. Everything will flow very nice. But the picture actually, it's want to convey an idea to you is that no matter what you do on a silicon chip, connectivity is extremely important to get performance and to get the function that you have. Actually, in talking with many of my American colleagues, they always tell me, well, Nani, no matter how nice is the device, if you cannot get the connectivity better, we already have system where you have 10 layers of metal to do connectivity, you would not really get any gain out of that, because there is a kind of under laws actually applied even to logic cells. It's the I/O that actually limits the communication into blocks. And that's one reason why people have been dealing with many structures related to communicating blocks in systems. We have seen a long growth in buses, in bus systems that actually now use advanced topologies, and also in protocols that are used for buses, advanced protocols for buses, as a part of this evolution to have better communication on a system. But eventually the idea that has taken place strongly in research and into the market has been the idea of the networks on chip. Network on chip goes back to some research that I did with Dalli and with Luca Benini at Stanford in around the year 2000. And the notion is very simple. It's that you have computational blocks on a chip. These computational blocks will be interfaced to a network where communication will be packetized, and this packetized communication will actually constitute the fabric that's on chip to transport information. Again, why to do that? It's smaller, it's flexible, you can cope with the inherent limitation of buses because performance and power of the buses does not scale up. In the world of the many cores, buses become a pain if not seen within the frame of a real network on a chip. Besides, there's one important issue. If you're using advanced technologies where the device may fail with a higher rate than usual because you're scaling down, things getting more risky. You have systems that are more and more complex, and possibly they become life critical because they have medical application. You want to have ways of controlling possible errors. Now, what is the industry that has been doing the best to control the errors in transmission? It's the telecom industry. We use the internet every day. We know that bits may be garbled when they go from one side to the other, but the end result that we get is correct, even when we do banking over the internet. These errors do not happen. Why? Because there are different layers in which corrections can be done. So by bringing the network concept also on a chip, you can have layered ways of controlling the errors, detecting, controlling the errors, so that you can have systems that are fully functional, even though you may have some local failures that can be temporary or they can be permanent. So how is the network on chip being built? The kernel NOC library, and it was part of the work that actually I did with Luca Benini many years ago, is starting from having the notion of switches, network interfaces and links, a library of this component that actually will be mixed and matched together to create the NOCs. Nowadays NOCs have additional blocks that are important because you have NOCs with firewalls, with frequency converters, controlling the width of the data, controlling the memory and so on, the on-chip interfaces. You can have different blocks to specialize the NOCs. The NOC technology had advanced quite a bit today. Now, the physical implementation has some aspects that are important. For example, the timing that can start from being synchronous, can be asynchronous, can be mesocronous. The notion of GALS is also very important for NOCs. GALS means globally asynchronous, locally synchronous, because you can have this notion of many islands on the chip that are synchronous, working on a specific frequency and in a specific voltage, and then having the NOC that does this asynchronous handshaking, and I would like to put here the work done, especially at CALT in Grenoble, on GALS for NOCs. Again, in this physical implementation, it's possible to introduce fault tolerance using coding, redundancy, or also packet retransmission. There are many ways of doing that. Now, can you design NOCs? What is the step in design NOCs? There is an important aspect which is design automation for NOx. Because design automation for NOx is the place and route of the 2010s. 30 years ago, we had transistors. The basic issue was where to place this transistor and how to connect them with straight wires. Now what we have functional modules, we have cores, we have ARM, we have MIPS, we have MPEG engines. We want to place them on a system and we want to connect them in an intelligent way with NOx. So the NOx design is creating this fabric that can be conceptualized by the engineer, but then it needs to be fleshed out in all its gory details by tools. So there are many issues because there's a large design space in designing with NOx, starting from the topology that you use, the mapping, which routes to use. Here you have two pictures, you're changing the topology, so the type of switches that are best to be used changes. And of course, being able to optimize the parameters. One of the big advantage and difference of a NOC over a standard network is that in a standard network you have standards, but the chip is a proprietary solution. So actually you can tweak the network and actually you can optimize local parameters. Optimize the, for example, the fleet length, the fleet size. Most designs done today are by oversizing the NOx so that you don't have problems in the implementation. But all these parameters can be tailored because in the end you want to have high functionality that can be done with a very limited energy. Because a lot of the market in electronics is mobile, and as we know, batteries are always a bottleneck there. And of course we want to simulate, verify, test. This is just a design flow diagram in small outfits of INOS, which actually was started with some of my former grad students. So how else are NOx? There's been lots of development in NOx. This is a series of chips done at KAIST in Korea over the years. This is a series of chips done at the last one is the Magali. It's a fairly complex chip that has all these galls built into that. Intel actually launched in 2007 the Polarity chip. That was the first one that really had enough 80 tiles connected by NOC, then went to cloud computing chips, and then Night Corners, which operates a chip for servers. It's all built around the notion system of a network chip. I can say today I just went through a simple exercise of looking at companies. Actually, 7 of the top 10 semiconductor companies sell products that have NOx in there. So NOx are there. NOx are there, are in products. There's still a lot of research to be done in order to optimize them. Really, the spectrum is to be able to use a NOx as a vehicle to obtain the best performance with a limited power budget. This is really the key. Again, I like to switch gear to say a few things about the vertical dimension. So, if you cannot put as many transistors as you like on a plane within this 1 by 1 centimeter, which is kind of the magic number before the cost of the chip goes too high, then you have to go vertical. And there's been a lot of interest into the 3D integration. So why people do that? They do it because you can get denser computational structure if you can stack chips on top of each other. And you typically would have shorter interconnection. And it's especially important when you have processor to memory system. So today, the main driver for 3D integration is actually improving processor performance by having processor to memory system that will connect vertically. You have the locality of memory, this cell locality in Z direction, in the vertical direction. But on top of that, you can do wide I/O. So you would not only save the power going through the I/O paths to go to the memory, but you can have multiple accesses to memory using 128 bit, and that's a vehicle to get much higher performance. On a different market, it's interesting to use the 3D technology to integrate, for example, digital and nano. Digital and nano that could be done with different technologies, and that actually are nicely packaged together for many products, like for example cell phones. Instead of getting crazy, you get this mixed signal chip where you have 2 different power supplies. You would actually get a package where you have stacked 2 chips together. Or possibly a third one with a micro antenna that's actually etched on a specific chip that will go on top of the stack. Now, of course, there are novel design challenges. routing, signal integrity, power distribution. One important issue is thermal analysis. I will not get into this, but there's lots of work going on in Lausanne, especially in the group of David Atienza, that actually deals with the fact that as you build computational structures that are denser and denser, then you do have the problem of extracting the heat. And nowadays people use techniques like, for example, having water flowing, or water or coolant flowing through your stack in order to cool it down. This is done, for example, in IBM. There are these chips done for servers that do use coolant. So your computational engine becomes similar to the engine of a car. You have the water going through the pump, the radiator. So your computer may break down because you have the water pump that has a problem. It's actually more likely to break down the water pump than the silicon itself. Of course, one of the issues is how you would do these structures so that they are configurable. So network on chip coming strongly again within 3D integration. You do not want to have stacks of chips where each die has been just designed for that stack. You like to have a mix and match of the different dies that you use there. And so you could actually have the notion that you put together a stack and then you use the network on chip to reconfigure the interconnection according to the application. So there is, of course, there's a lot of interest in 3D NOC design. One of that is to use NOC, network on chip, to support the wide I/O, to support smart ways of connecting to the memory. And you have many challenges there. Of course, you have to meet the application constraint in the 3D structures, where you have bandwidth, latency controls, and also you have to deal with 3D technology constraints because the vertical connection is nice but comes for a price. You have to use this TSV through silicon vias that are much bigger as a footprint that we would like to have and much more prone to failure than what we would like. So again, they're using redundancy, using schemes by which if a path, vertical path doesn't work, you can route around. It's extremely important to get a successful system. Now, I'd like to say a few words about nanowire systems. This is a picture from the top of a sensor. And I will introduce it by starting from the 3D paradigm, okay? Once you have a system, a memory, and the analog counterpart, it's interesting to say, can I make my system complete by having a layer on top of the analog that can be able to recognize the environment? For example, being able to sense if some specific chemicals are on top, if some specific biocomponents are put on top of the chip, and therefore have a full 3D stack. And there are many ways of doing that. Whether that makes sense or not, it's too early to say. Of course, the semiconductor industry would love to have 3D stacks that are used for medical analysis, where chips that are used where you put saliva on top of it, or urine, or blood, and you can use them only once, because even though you might clean them, and you can do that in the lab, nobody would like to go to the doctor and use a chip that's been used by somebody else before. That would not look nice. So that would lead the way to have products that have a high volume, and that would help bringing down the cost. Conversely, from a scientific point of view, it's extremely interesting to look at how you would make these disposable layers. So how you can come up with a combination of two parts, one which is electronic with the software built into it that does the computational part, and then has a layer on top that is the sensitive part that then can be peeled off and thrown out. And so the only part on the top is the one which is sensitive to the chemicals or to saliva or to urine or to blood. So this also is an extremely important concept. Now, where do these electro-biosystems fit in? It's basically a system that do electronic processing of biological information. They have to work mainly autonomously without human intervention, and they have to work in real time. So the idea is to replace the tests that are done in the labs. And you can use again the same paradigm. When a computer used to take the space of a room, it costed a lot of money. When you could miniaturize the computer to have it as a portable, the price dropped a lot. The same thing, if you think of a medical test that happens in a lab, you have to pay for the technician time, for all kind of machinery and energy to drive this machinery. If you can do that on micro samples that are done on a microchip using microfluidics, the cost is likely to be much less. And the ideal thing is, of course, to bring the notion of the test to the point of care. So you go to the doctor, you do the test there. You would have an electronic signature of the test. The doctor will interpret it. I will never say that you have to replace the doctor by a human, otherwise I will be shot immediately by my colleagues that actually are on the other side of the city and work in a different university. But there can be this tremendous support of electronics, and actually the fact that you can have this notion in real time. And the same thing can be applied to the environment. So the targets that you want to send, what you want to send, DNA, viruses, proteins, also non-organic components of different types. So the full notion is, in the end, is to build integrated sensors. This is an example of a lipid biolayer with ion channels that, for us electrical engineers, looks like an impedance. There are some RNCs, and these are vary. And if you have specific protein that will actually come in and stop some of these ion channels, then you will have a variation of impedance that can be sensed in some path and can provide a signal that electric will tell you whether that compound is present or not. Interesting enough, these nanosensors also can be built in a way to be efficient using nanostructuring. So you can actually have sensors that are built on top of CNTs that will give you larger surfaces, because just CNTs are three-dimensional and are very small, and also because the conductivity is very good. Every time that you have a target that attaches to a probe, you have to catch a couple of electrons. You don't want these electrons to be lost. You want basically to collect efficiently the electrons that are generated by a biochemical reaction, especially if you want to work on small quantities. So what's the end result? If you use nanostructuring of electrodes for biosensors, you would have, in the end, more electrons, more current, so more sensitivity. So basically, a small compound can be sensed because you can get to a current that it can still measure within the noise limits. So again, what was in the past not measurable, now it is measurable because you have measurements in the physiological range, which is of interest to medical doctors. Again, this picture here shows actually how these devices are done, by depositing on the bare electrode the nanotubes, and by depositing on that the probe, which in this case are enzymes that then can be used to collect a specific target that has some affinity that will combine with the probe. So one important concept here that I like to convey that relates to systems. Much has been said about system in ASICs and platform-based design. So if you look at biosystem, one important thing is the cost that you need to bear in order to break into a market. Where are these biosensors present? They are present where you have a market which is unfortunately related to a pathology which is well diffused. And that's basically glucose sensors, because there are many people with diabetes, and the number of people who have diabetes is increasing, also because of obesity, especially in developing countries. And so there's a market there. Also, we know that the glucose sensors today can be bought from China at a fairly low price. Now, the question is that there are many other things that are interesting to detect in a human, for example, concentration of lactate, concentration of other glutamate, uric acid, and so on, that could be good for having diagnosis, advanced diagnosis, also for measuring wellness, how people do well, how people support stress when they play sport, how far should you play sport until you are in the enjoyment range and you don't go into the pain range, and you realize, of course, the pain the following day. So the idea is that in order to make this affordable for an industry to be sustained, you have to design also biosensors in a modular fashion. You have to see a system as consistent of components. We know how to handle the software component, the digital component, the analog components, but you can handle in the same way the probes that can be seen as cells that can be micro-machined and that can have standard size, and actually by using different types of components, like different types of enzymes, can be targeted to different types of compound to be sensed. So you can have one way, think of the old way of using standard cells to do systems, to do nanosystems that are done for addressing biological problems. This, in my opinion, it's a tremendous opportunity to bring the cost of this system into a reasonable range. And it is doable. I'd like to close this talk by talking about some application of this nanosystem in general. This nanosystem can be, of course, be applied in many places in the health industry, because we see you can actually sense, you can do a point of care for the environment, to check for weather, to check for water pollution, for security, for, of course, computing, communication, control, and for defense. I'd like just to make a couple of examples coming from a program called nanotera.ch that I'm running. So now I'm a little bit flying out from what I do as research, which is what I mentioned in the past in this talk, and what I manage as a large program that's throughout all Switzerland, that actually helps to fund research that mixes nanotechnologies on one side with system technology, software system application, in order to address issues related to health, environment, and security. This program, it's a fairly large one, runs at a run rate of 50 million francs a year, and it basically revolves around 20 major projects that are multidisciplinary projects that are happen with colleagues all over Switzerland. So in electronic health, many issues are basically related to biosensors, I mentioned before. Body area network technology is extremely important. Smart textile. Doing clinical support, for example, doing remote diagnosis and using drug delivery techniques. The picture here shows actually a membrane that can be electrically open or closed, and it's a way to actually deliver a drug in a specific position of a body. Prevention is, of course, extremely important too. Challenges here are being not invasive and also being safe and secure. So it's interesting how there is a migration of concerns from one domain to the other. You start working on biosensors, then you use biosensors as a way of doing implants in the human body. And there you realize that there are security concerns, and therefore you have to address security by using specific technologies that are typically related to the security domain, to hide some information, to make it available to some doctors in case of emergency, and that's extremely interesting. An example here creates one project that deals with doing an implant. This implant is meant to be put into the interstitial tissue, so it's something of, you can envision that as a cylinder of 2 millimeters in diameter and 2 centimeters in length. This can go under the skin, can be injected with a syringe. This is power from the outside, so you would have a patch that you would put on the skin. This patch sends in a EM field that's enough to power the sensor, and through backscattering to get the information out, that then from the patch can be transmitted to a cell phone, and that's a way actually to do remote measuring, because then the cell phone can be connected to the internet and feed information to the doctor. Another important example within this nanotera is this project actually, which is led by Tröster in Zurich, that it's to do intelligent textiles, textiles that actually can sense pH, humidity, and one specific embodiment is to do underwears for paraplegic, for elderly or chronic patients that don't move in the bed. You know that if you don't move, you can develop these ulcers that are the cubitus ulcers that are extremely painful, and it's fairly straightforward to detect them with a fabric like that. The question is to make the fabric low cost and convince people to wear them. It's a very simple technology, but it can have a tremendous impact because you would know in advance when you have to move a person to avoid ulcers. In the environmental domain, of course, we look at issues related to monitor heat, wind, vibration, controlling pollution. Actually, this picture was taken, I took it myself after landing in Shanghai, and I was terrified by the idea that these people with the mask will come there, sense the temperature from my skin, and if there were 3 options, either they let you alone, or they just measure a temperature with another device, or they stick a pill in your mouth. So I think there should be a better way of doing that, but if you think about it, airports are the worst places for biocontamination. And people should be concerned about that, and probably they're more concerned in Asia where there's more traffic and more risk there. And of course, this technology can be used for emergency relief control by if you have any catastrophe, how to react to that. Again, challenges is to be seamless, to be in the environment, not to create damages. So to give an example, I'll just mention the cross-sense project done by Thiele in Zurich. You see, this is the Switzerland as you like to see it, with the Cervino, the Matterhorn, covered with snow.
this is the mountains how we don't like to see that. That's actually, this is a rock fall, and after a while that station up there with the funivia, it's going to drop down. It will not last that long, and that's another rock fall there. So the idea is, of course, to instrument various parts of the Alps with devices. This one picture there of a device which is self-powered, to be able to measure the movement of the glaciers. Now, this is extremely complicated because you have to have local measurements, you have global measurements that are done via satellite, and then you have to integrate these measurements into some geomechanical models that will give you the compression and the risk that you would have a rockfall. There's a network actually that's being deployed in the Mattertal, that's the valley that goes up to Zermatt, and if you ever drive there, you know that you typically drive fast because there are rocks falling up there. It's very dangerous as the valley itself, and of course it's a big concern for Switzerland because nobody would ever like to close that to the train or to the car. And besides, this technology in Switzerland is extremely important because there are other areas where the effects of global warming are important. Last example is Open Sense. It's again a project to measure pollution. This is a city with pollution. It's what we would not like to see. How do you measure pollution? You do it by using devices. This is done in Lausanne. These are devices that go on top of buses, so the buses goes around the city, make samples and transmit these signals back. These are in red are the routes in Lausanne that are covered by the buses that are gracious enough to have our devices. Again, this is a project where you have a physical part of gathering information, but the challenge is in the system and software. You have information which is given at various moments, which is incomplete, which needs to be integrated in order to give the global picture. So the amount of software research there, especially in the group of Boy Faltings and Karl Aberer, is extremely important. Last point before I close. All these techniques that are related to health and to systems are very much related to the notion of human enhancement. So there is this deep interaction of nanosystem with humans, and if you look at the current frontiers of, for example, of medicine, you see these systems that are implanted in the brain to try to cure Parkinson, Alzheimer. There are important studies done, for example, at Berkeley to do this very small power radio that could go inside the brain because you don't want to have connection between the brain and outside in terms of wires because of infections. Prosthetics is a very important field, how you connect electronics to artificial limbs, how you would build eventually an artificial organ, because an artificial organ is nothing but a device where you have sensing, electronic, and then some sort of actuating to produce or to put into the bloodstream some chemicals. Now, the key issue here that's interesting is where do we stop or what our horizon is? You know, we all start by the notion that we want to correct deficiencies because we like to live in the standard way. So I don't see that, well, I get eyeglasses. People have been using eyeglasses for 1,000 years. Nobody complains about eyeglasses. Same thing as what you would use for the deaf. But what happens if you just push these devices to make you a superhuman? Well, of course. There are many ways of doing that. Think, for example, of audition devices that has signal processing so that you can do real-time translation, or you actually can zoom in on the speech of this person. So you would be able to listen to somebody. That would be great for politicians that actually can try to listen to somebody and shut off the other ones. There's been the famous case of Pistorius, who actually lost a leg and got an artificial leg, then he was told that he couldn't run among the handicapped because he was running faster than normal with this artificial limb. But actually I think that we will face more and more of these problems, and this is a very interesting challenge from the ethical standpoint. So for those people interested in this, you can refer to an issue of Spectrum on the singularity that came out actually last year. So in conclusions, nanosystems exploit new technologies and new devices. I gave the example of two types of technology devices, the silicon nanowires and the carbon nanotubes. I say that they're interesting because they support two features that typically we don't see in other devices, the ambipolarity and the memresistivity. The ambipolarity can be used to make circuits more effective, to implement logic of various type, to kind of unify the data path design and the control design in a single way. And memoristic effects are useful to provide the primitives for doing new types of memories. And those, again, to some extent are there, and with more and more nano devices coming up, they will be actually prominent and will be there on the market. Talking about how to use these devices, I didn't spend too much time talking about nanoarchitecture, but I made a few points. The notion that things have to be extremely regular, because wiring is what kills performance. So these gate array-like styles, the possibility also of using these new devices to build new families of FPGAs that can be more flexible. And then, of course, the look and the search for building systems that are three-dimensional, because the third dimension can give specific advantages with respect to heterogeneity, so analog biosystem on top of digital, as well as providing much better processor to memory system, which is actually one hot issue in 2012. And finally, I wanted to make the point that we will see more and more hybridization of technology. So bringing onto CMOS more and more devices. People who actually work in process tell me that at least 52 elements of the periodic table are used in CMOS today. I think there will be more tomorrow. We know that we can go up to 92, but 52 seems already a lot. I think that the challenge there is actually to build this nanobiosystem that can probe, can interact with the living matters, because this can give us a new perspective. And this type of electronics can have really a profound impact on the health, on the environment, and actually will put electronic engineers on the driving seats for the research that is coming up in this century. Thank you very much.